Hey Tim, with all this coronavirus going around, let's have a look at exponents and logarithmic functions a little bit more closely. Bring your mask. So we're familiar with geometric progressions where ui equals some constant times another constant r to the I, where I is 0, 1, 2, 3, 4, etc. Now I could be any number, so why don't we give it an x? So we can say y equals coefficient a times b to the x. And this graph just shows an example here. We've got y equals 2 to the x. You can see how it grows exponentially. And then there's another graph I've drawn here, which is also an exponential graph. But it's decaying. Why? Because b is less than 1. So you can see it's getting smaller and smaller. So we've got a half to the x here. You can also write that as y equals 2 to the minus x. Why is that? Because a half is 2 to the minus 1. So 2 to the minus 1 to the x equals 2 to the minus x. So you have these two graphs that are mirrored around the y-axis. Y equals 2 to the x and y equals 2 to the minus x. And let's have a look at the logarithmic function, which is the inverse of the exponential function. So if I have y equals b to the x, how would I write that if I was looking for x? I'd have to say x equals log of y base b. So the log is the inverse function of the exponent. And one needs to be able to flip between the two. If y equals b to the x, then x equals log y base b. Look how that b is at the bottom of the log. And it's also the bottom of the exponent. So one must always just look at that. Practice changing these things from one form to the other. So for example, if I have y equals 2 to the 3, we all know that's 8. So I can say write that as 8 equals 2 to the what? But if you don't know what that is, if it's a more complex number, maybe y was 10 or something, you'd need to put in your calculator as log of 8 base 2. See how the 2 has come down to form the base of the log here. So x equals log of 8 base 2. And in the general form, y equals 2 to the x, then the inverse of that function is y equals log of x base 2. Now if we print that graphically, our exponent function, y equals 2 to the x, looked like this. It was growing nicely as x increases. And to find the inverse, we always look at what it looks like as a reflection in the y equals x line. So let's just reflect that, and we'll see there. That's plotting now y equals log of x base 2. There's some interesting things to observe here. For example, the log of 1 is always going to be 0. Okay, because just as y equals 2 to the 0 is always 1, if you reflect that, you'll see that the log of 1 is always 0. And similarly, the log of b to the n is always n. So if I say the log of 2, I'm going to see that it's 1, because it's the log of 2 to the 1. If I say the log of 4, the log of 4 is log of 2 squared, and it's 2. See how the log is n in every case. Then there's just a 10 to the x. Y equals 10 to the x. When it's the base of 10, that's a special case, and we don't need to write the base. So here we just say log of y equals x. It's just understood that if there's no base, the base defaults to a 10 over there. That's not too complicated. Let's have a look at some of the log basics. We already know that a to the m times a to the n is equal to a to the m plus n. And also, a to the m to the n is equal to a to the mn. So these are important rules that one needs to apply when you're working with logarithms. Now the first log rule is the power rule, and it says that log x to the n is equal to n log x. We've actually just touched on that looking at that graph. And then there's the nth root rule, which says the log of the nth root of x is equal to 1 over n log x. Now you'll notice I didn't put the nth root rule in bold. Why is that? Because it comes straight from the power rule. Because the log of the nth power of x is equal to log of x to the 1 over n. And you're just bringing that 1 over n to the front, just like the power rule says you must. Then we have the multiplication rule, which says that log of pq equals log of p plus the log of q. Now that's kind of counterintuitive. We're turning a multiplication into some form of addition. And we also have the division rule, and I haven't put that in bold either. Why? The division rule comes straight from the multiplication rule. So if I have log of p over q is equal to, I'm going to cheat a bit, it's equal to log of p minus log of q. Now why is that? If I can write log of p over q as log of p times q to the minus 1, which is equal to, using our multiplication rule, we say that's equal to log of p plus log of q to the minus 1. But now we can take our power rule and we take the minus 1, put them in front, and we're left with log of p over q equals log of p minus log of q. You can see how that comes directly across there because the minus 1 goes to the front. Now, there are a couple of things you must watch out for. Because when you're faced with a sum, you want to do something. And sometimes one tends to rush into things that are not allowed. So you cannot simplify log of a plus b. Only the multiplication and division. So log of a plus b is not equal to log a plus log b. We've already said multiplication is that. You cannot simplify that. And also, just remember that a plus b to the m is not equal a to the m plus b to the m. That's not what the rule says. So stay well clear of these common mistakes. Why not? This guy's got middle terms, remember? You're multiplying all those brackets out. You know it well, but yet just be careful. So when you're working with logs, here's a tip. Not always, but mostly, convert logs to powers. They're much easier to work with. For example, the power rule. Show that log of x to the n equals n log x. So, first of all, let's get away from logs. How do we do that? Well, let's make log of x base b equal to some arbitrary number r. Now, using our swivel method, we can say that x equals b to the r. See how b is still the base? It was the base of the log, and now it's the base of the r. So x equals b to the r. Now we can say x to the n equals b to the r to the n. And using our power rule, we know that it's just rn. So if we take logs now on both sides, log base b of x to the n is equal to rn. See, I've swiveled the b back down to the base again, which is equal to n times r, and r is log x. So there's our proof. Log of x to the n equals n log x. Now, wasn't that simple? Well, maybe it wasn't. But let's say you got it wrong and you couldn't remember the rule. Yes, even when you get it wrong, when you get away from logs and you write it as a power, things generally unravel and you're able to do the proof. For example, let's say I'd said, I'm trying to prove the power rule again. So I'm trying to prove that log of x to the n equals n log x. Let's say I'd picked log of x to the n equals r. Now the book says I must take log of x equals r. But let's say I'd said log of x to the n equals r. I still write it as a power. So I say now x to the n equals b to the r. So what is x? X equals b to the r over n, because I'm taking the nth power now. So now I've got log of x. I take logs on both sides, so it's simply log of x equals log of x, I bring the b down, log of x equals r over n. So n log of x equals r. Okay, I just times everything by n. So n log of x equals r, but we know that r equals this guy. So I've just proved it. So log of x to the n, which is r, is equal to n log x. I hope that just illustrates how moving away from logs and expressing things as powers can lead things to unravel. Let's look at the multiplication rule. Show that log of pq equals log of p plus the log of q. So we write it as log of p equals some arbitrary number r, and log of q equals a number s. Let's look at the multiplication rule now. We want to show that log of pq equals log of p plus the log of q. We write this as log of p equals some number r and log of q equals some number s. Now generally in maths, when you're trying to do a proof, you don't want to be introducing more variables. But in this case, we want to get away from logs. And that's the basics, the basic approach every time. So let's write p equals b to the r and q equals b to the s. So what is pq now? Well, pq equals b to the r times b to the s, which is equal to b to the r plus s. See there, now we're already adding r plus s. And if we take logs on both sides, we've got log of pq equals just r plus s. See how the b's swivel down to the bottom here. Okay, so log of pq equals r plus s. So log of pq equals, well, r is log p and s is log q. And we've just proved our proof. Here's another sum, which is quite a tricky one at first glance. Okay, what is find the connection between log of c base b and log of b base c. What? You got to be kidding me. Right, let's write log of c base b as r and log of b base c as s. See, the approach is the same. You want to get away from logs. So c equals b to the r, bringing the b to the base of the r there. C equals b to the r and b equals c to the s. C is b to the r, but b is c to the s. See how we can get rid of a b in the c equation. So we take that guy, we say, well, that's b, c to the s, we put c to the s there. So c equals c to the sr. And also b equals b to the rs. So now we're starting to think, yo, that means that c to the 1 equals c to the sr, which means that sr equals 1, and this means that s is log c and r is log b, and they must multiply together, must give you 1. And that's the connection between the two, which was what we were asked to prove. So these things look quite complicated, and sometimes you have to do a bit of mental flick-flacks to get them right. But in most cases, there's one step that you need to find. There's one step, and then you've solved the whole thing. So these guys, you're only going to learn how to do them well by practicing. So do a lot of these sums. Maybe look at examples first before you jump in. But generally, if you get away from logs, write it as an exponent. They tend to sort themselves out. And there's another tip. And that is, when you're working with logs, it's often a very good idea to express them as powers. So for example, here I've got log 16 base 2. That's log of 2 to the 4 base 2. But now we've learned from our power rule, that's 4 log 2 base 2. But log of 2 base 2 is just 1. So that's 4 times 1. Here's another one, log of 1/16 base 2. Well, 1/16 is 2 to the minus 4. Bring them to the front, and you've got log 2 base 2 times minus 4. It's just minus 4. So often these things unravel simply by expressing them as their powers. Here's a difficult one. What about log of 8 to the base 2.5? Wow. Let's write, so we've got that's equal to log of square root of 2 of 8. Okay, but we know that 8 is made up of 2's, so we can say that's equal to log 2 to the 3 square root of 2. It would be nice if we could express 2 as a square root of 2. Then we'd have 1, because the log of b base b is 1. And what we can do then is we can say log of square root of 2 to the 6 base square root of 2, and that's equal to 6. Here's another example. Express log 64 minus 2 log 4 plus 5 log 2 minus 10 log 10 to the 6 as a single log. Okay, here we're just using our multiplication and division rule, because log of 64 minus log of 16, okay, so 2 log 4 is just log 16, plus log 32, okay, because 5 log 2 is log 32, minus log 10 to the 6. And if you put them all into your multiplication and addition, where minus is division, there's 2 minuses and 2 multiplications, you end up with this big number, and you're taking the log of it, and it simplifies down. You could have also expressed it as powers of 2, and you can take that sum a bit further. Let's look at logs and inequalities. For example, a unit of an isotope decays to 0.917 to the t units over t days. When will it fall to 0.1 units? Sounds complicated, but one first needs to notice that it's of the form y, the number of units, is equal to ab to the t. It's just a standard exponent, and in fact a is 1. There's no a in front of that term. So we just have y equals 0.917 to the t. Now we want to know, when has it got to smaller than or equal to 0.1? So when is y equal to 0.1? So 0.1 must be bigger than or equal to 0.917t. Now we take logs on both sides, which we're allowed to do. And so we have log of 0.1 must be bigger than or equal to log of 0.917 to the t. This means that log of 0.1 is bigger than or equal to, let's move the t to the front using the power rule. So we have now t times log of 0.917. Now pay attention. Log of 0.917 is less than, it's negative, it's less than 0. So when we divide him, we must reverse the inequality. You must watch out for this. All these sums, when you're working with this, often they lead to the switching of the inequality. So watch out when you divide by log of a number that's smaller than 1. Remember, log of 1 is 0. Log of less than 1 is negative. Log of bigger than 1 is positive, and you don't have to switch the inequality sign. Here's another little, just an example. A quarter to the 2x minus 1 equals 7. How do we get to that x, 2x minus 1? Well, we're going to take logs, base a quarter. You see the base there comes around, so log of 7, base a quarter, equals 2x minus 1. That's just a number. You can put them in your calculator, and you can rearrange your terms and find x. So working with logs is quite simple. One just needs to be able to swivel between log and exponent, and there's a few little tricks applying the power rule and also multiplication division rules. Lastly, when we're working with logs, we want to plot a couple of graphs. And the exam question will always ask you, plot the appropriate graph. So first of all, let's look at the graph of exponential growth. We've seen the graph, how if you have the form y equals ab to the t, it grows, and it's got this nice constantly increasing shape to it. What's the changing variable here? T is the variable. A and B are just constants. It's complex to plot these graphs, okay, and they grow very fast. It's very difficult to look at them and see where's this graph going. But let's take logs on both sides of the equation. So we take log of y, and we take the log of ab to the t. Because we know our rules, we say log of y equals log of a plus, move the t to the front, t log b. Okay, log of y equals log of a plus t log b. Now look carefully here. Do you see that this is of the form y equals mx plus c? It's just a straight line graph. If we were to plot log of y instead of plotting y and against t, so we take the log of y, but we do not take the log of t. We just plot t as he is. That's my x. That's my y in the straight line. Okay, we plot log of y against the variable. In this case, it's actually t. And then we've got an m and a c. Now, what is m? Well, m is simply log of b. Okay, and c is log of a. So if we were to plot the graph and look at the graph, we could then see wherever it cuts the log y axis. Okay, we're plotting the y-axis as log y now. wherever it cuts that line, that is log A. And if we know what log A is, we can quickly work out, okay, so that's the C. The C value becomes log of A. And if we know log of A, because we know C, we looked at the graph, we know log of A, we can work out A. And we can start building our function. Also, M equals log B. So we can work out M by looking at the graph. We get a value for M. We take that value and make it equal to log B. And there you go, we can find B. Now we have the equation of our exponent. So what would typically happen in the exam situation, you'd be given a table of values of y versus t. Y is a function of t. And you then need to work out, well, what is log of y? And you plot log of y against t. That'll give you a straight line. If it's not a straight line, it was never an exponent. And that they may even ask you, they may say, is this correlation really exponential? And so you plot log of y against t or x, and you'll then say, yes, it's a straight line, or it's not a straight line. And if it is a straight line, you can easily find m from the graph, and c, where it cuts the y, the log y axis. So these things are quite simple. One needs to understand where they're going though. Okay, so that's the first case of plotting exponential graphs. Then there's also a graph of the power law model. And this is of the form y equals ax to the n, all right, where a and n are constants. So y and x are variables. So again, this is also a complex one to plot. You're not going to get a linear graph. So let's see what we can do with it. We take logs on both sides, and we then see that log of y equals log of ax to the n, and that reduces to log of y equals log of a plus, bring the n to the front, n log of x. So we're using our power rule combined with our multiplication rule. Very simple. Now let's look at it again. You're right. Y equals mx plus c. What is c? C again, same as before, is log a. But what is m? Well, m now is simply n. Okay, and log of x is now my x that I'm plotting. So in this case, you'll be given a set of values of, say, y and x, and you're going to draw another two columns. You're going to plot, and you're going to calculate log of y and log of x. Put them side by side, and you plot. Rather, instead of plotting y and x, you plot log of y and log of x. This will give you a straight line graph. You look at your straight line graph and you read off your c value. The c value will give you log of a. And when you know what log of a is, you can work out a. And you work out your gradient, change in y over change in x from your straight line. That'll give you m, and m is n. Now I can write my power law equation. Y equals a, which I found, x to the n, which I found. So always, when you go into this type of a question, ask yourself, is this a power law model? In which case I must plot log of y against log of x. Or is it exponential? In which case I must plot log of y just against x. And that's all from me. Thanks very much. Feel free to contact me if you have questions, or if you want to do some examples. If you're struggling with a particular example, you can email me and I'm more than happy to help. Thanks a lot. Ciao.